supposed to be a learning exercise. You try your hardest because you've got the mindset that it's a quiz, and now we go over it, and you can now this is where you're gonna figure out where you were going wrong, and we're gonna really correct that and learn, right? So the whole thing, this as I go over it, this is a learning experience. All right, so the sequence of changes in height, and so before the quiz I asked you, how do we find changes in height? Or how do we find a change in the dependent given a constant rate and changes in the independent? We use, you should have been thinking this, right? dy equals mdx. dy equals mdx. If you have a constant rate, you have a change in your independent variable, m times dx gives you the corresponding change in the dependent variable, and this is what these are asking for. Changes in height based on these rates, these constant rates. Okay? This is a recurring theme all semester. A really important idea. Okay? So the first change in height would be negative 0.75 times 0.15. Whatever that turns out to be. The next change in height would be negative 0.75 times 0.15. Third interval. Yeah, we use this would be using the rate at the left side of every interval. So it'd be negative 0.5 times 0.15. Then negative 0.4 times 0.15. And then back to negative 0.75 times. So each change is calculated by m dx, and dx is just 0.15 every time. Hopefully high success on this. Hopefully high success. Okay? Expression for the series. So what's the associated series? How do I express the associated series for this sequence? Add them up. Add them up. Someone said add them up. That's the best answer I've heard all day. So it's going to be that plus that plus that. I'm not going to rewrite them. So for instance, this would be an example of something we might actually grade for some credit points. Did you take whatever you wrote in part A and then just show it as all of them added up? Because we hammered that on Friday, that's what a series is. You just take all the terms of the sequence and you add them up. Okay? And then finding the value would just be using a calculator and you get something. Okay, so you get some number. And what would that be? That would be the total of all the individual changes in the 5 intervals, right? You'd be totaling up, so we'll keep that in mind for later. You'd be totaling up the individual changes in the 5 intervals. And that would be what that value is. Okay? So what would this be? The sequence of partial sums. So now I'm going to rewrite this as, so we'll just say, I'll just say A1, A2, okay, so the first 3 terms of the sequence of partial sums. First is A1, second is A1 plus A2. And the third one is A1 plus A2 plus A3. So just showing 3 terms is enough to see whether you got that or not. Of course, the fourth one would be A1 plus A2 plus A3 plus A4. And then the 5th term would be the same as the series. It would be the sum of all 5. Okay, questions so far? Anybody have a question? Okay, so the next part D was, what's the meaning then of this value in the flag context? What's the meaning of that value? And if we take all these changes from each of the 5 intervals and add them all up, then what do we get? Yeah, Kellen. Yeah, well said. So he said it's an approximation of the total change in height from 0 to 0.6 seconds, right? Because we're adding up all the changes to get a total change, right? A total change in height. So that would be the first part of D. Second part of D was same question now for this. What does this sequence, what idea or thing, does this sequence represent? Something we've been working hard on a lot of the semester. Anyone get this? So what do we got now? We have what? We have A1, which is what would be the change after going through one interval. And then A1 plus A2 would be what? The change for the first two intervals, right? The accumulated change, right? The accumulated change. And then this one would be the accumulated change over the first three intervals. So what is this idea? What is this sequence kind of representing? Anyone? Someone said over here. Net accumulation function. Net accumulation. This is a representation. This sequence is very much like the idea of a net accumulation function. When you've gone through so many intervals, how much net change do we have from the beginning? Right? So this is like a net accumulation function. But like a discrete version, right? Like instead of a continuous version of it, it's just at certain things. Yeah?
Would that be considered incorrect if you said total accumulation? Because I assumed it was total because we started at 0.
Well, so the key here I'm looking for is function, right? So if you wrote total accumulation function, then that's pretty good. But if you just wrote total accumulation, that sounds like what single value. That kind of sounds like more like part B. Because B is like the total accumulation for this whole interval we're looking at. The idea of function is you go as far as you want into the interval, and it gives you how much change you've had so far. And so given any amount of time, how much change have you gotten to that amount of time? So the idea of function. Okay, questions on A through D? A through D. Is it making sense? Okay, so now the second part. All right, so how do we do on part E? So we've got this exact rate function, R sub h, and we want to represent constant rates that are trying to approximate R sub h, right? We want to use a left-hand approach with intervals of 0.1 seconds. So using my hint here, the first interval goes from what to what? 0 to 0.1. So using a left-hand approach, how do we represent the constant rate that we're going to have in that interval? Anyone get it? RH of 0. Function notation, right? It's been a huge theme this semester. R sub h of 0 then is the exact rate at the left side of that first interval, which we're going to make the constant rate for the whole interval. Just curious, how many people got that? Not enough. Okay, so this idea of function notation gives us the value of the dependent variable for a given value of the independent variable. So we've worked hard on this, so hopefully we're still improving on that. All right, in the second interval then, what will the constant rate be? R sub h of 0.1. Use the left side of the second interval as 0.1 seconds. So we take that rate, R sub h of 0.1, and we say that's the constant rate for that whole interval, okay, etc. Now we're not going to write 60 of them, obviously, but we can write a few. So that's the first four intervals, and then we can say dot, dot, dot. And what will the last one be? R sub h of? Okay, so 60 intervals of 0.1 seconds means 6 seconds, and then the left side of that last interval will be at 5.9. Bonus, if you got that, wow. Good job, extra credit. What I'm most interested in here is seeing if you got this going this way. But that last one would be R sub h of 5.9. Okay, so now the approximate changes based on those rates. So if in the first interval we have this constant rate, then how much change do we get? That, what? Times 0.1. So the constant rate times 0.1. So there's our first change. The interval, the change in the first interval due to that constant rate of R sub h of 0. Next one. So if you didn't get it, learn it. That's why I'm going over it slowly. Take notes. Learn it, right? Super important. All stuff we've seen before. Now applying the ideas of series and sequences to stuff we've seen before. Super important. All right. So then the next rate was times. Again, the interval width stays the same, so our dx stays the same each time. So we're just doing, again, m dx, m dx. Third interval will have this much change associated with it. Dot, yeah, dot, dot, dot. Okay, so now can we come up with a formula for that? Can we come up with a formula for that? So look, which interval is this? This is the first interval. This is, or say, I equals 1. Second interval. Third interval. So what's the only thing changing here? What's the only thing changing in these terms? The input into the rate, right? So when I is 1, we get 0. When I is 2, we get 0.1. When I is 3, we get 0.3. So that's where the formula comes into this. We're always going to have an R sub h of something times 0.1. That's going to be the general structure of this. It's just what is the of something. So R sub h of something times 0.1. So 1 gives 0, 2 gives 0.1, 3 gives 0.2, 4 will give 0.3. So what is the formula? I minus 1. So it's always 1, like the 2 gives kind of a 1, 3 gives a 2, 4 gives a 3, so I minus 1, but then divided by 10. All right, so did anybody get that? Make it all the way and get that formula. Some of you, good, good, really nice. That's hard, okay? That's hard because there's a lot of things you had to get right along the way. So if some of you got that, that's impressive. That's really good. But the rest, do we understand it? Could we do something similar? Or can we recognize what's happening here? All right, so this associated series in 2 ways. So without writing it. So what the one way to be would just be to show these all added together. R sub h of 0.1 plus that, etc. And then we could also use summation notation. The sum as I goes from 1 to 60. This is a finite sum, right? 1 to 60 of that, right? That thing right there expresses what? Adding up all of these. Adding up that, plus all the way to the 60th one. All right, questions? Anybody have a question? Last chance. Okay. Yeah. D. Oh, up there. So D. So the series was the sum. The series was the sum of all the changes in each individual interval. So then you're getting a total change over all the intervals. Each. Talk to me after class because we lost track of it. So ask me, when it's more pertinent, and then just ask me after class. Okay, so I have another activity for you to work on here in groups. Okay, so see if we can get through this. So turtle is walking across your back lawn. Everyone has the turtle walking across their back lawn, right? And then on day 1, he starts at the east end, and he walks halfway. Okay, on day 2, he walks half of the distance remaining. So in other words, he walks an additional quarter of the way, right? So he walks half of what's remaining. And then on day 3, he's going to walk half of what's remaining, or what, an eighth of the total width. And he's going to continue that way, always walking one half each day, walking one half of the distance remaining to get to the west end. So I want you to write a sequence of the distances walked by the turtle each day. Express it as a series. We're going to do the sequence of partial sums, the general term. Go, you can do it. So this is, we can finish this today. We can do it.
No, that's because for BS. No, the summation of the list.
So given those I values, 1, 2, 3, 4, what do we do with I to get the ith term? 1 over, you should have 1 over 2 to the I. Did you get it? 1 over 2 to the I. Or 1/2 to the I is also a way to say that. 1/2 to the I is the same. Yeah, so if you want, and then if L is the length of the lawn, you could have those all multiplied by L. Okay? So if L was the length of the lawn, you have L times every one of those terms. And then you just have L times L over 2 to the I, if you wanted. Or L times 1/2 to the I. Okay, in the sequence of partial sums, we have 1/2 and then 3/4. 1/2 plus 1/4, 3/4. And then 1/2 plus 1/4 plus 1/8, right? Sequence of partial sums. It's where you, each time you go to the next term, you add one more term of the sum. Anyone got a formula for that? So in order to do that, we need to find what those all equal. So 1/2, 3/4, 7/8, 15/16. Is that right? Anyone come up with a formula for that sequence? Yeah. 2 to the I. He wants 2 to the I minus 1, so he's seeing that this is like 4 minus 1, 8 minus 1, 16 minus 1. Good? All over? Does it work? I think it works. And then if there's an alternate, you could have said 1 minus 1 over 2 to the I. That's also the same thing. You could have said 1 minus 1 over 2 to the I. So that's the formula for the sequence of partial sums, right? So this is the formula for the original sequence. We build the sequence of partial sums. It has a formula. All right, so what about the turtle does the sequence of partial sums represent? So this sequence right here, how could you say what that means? What does that sequence mean or represents? Net accumulation function of the turtle's distance. Yeah, or just like how far he's made it. Exactly. So how far he's made it after day I, right? So after day I, how far across the lawn he's made it. Which is, that's net accumulation of distance. Okay. Question, will the turtle ever make it to the wall, the west side? Yes or no? Stay tuned. We'll answer it mathematically.